Hey, welcome. Just a nice quick one. Only got an hour before tea tonight, but I'm just going to do a quick one. Basically, we have this Mega Drive VA4. I'm starting to do more mods on them as we go. So this is the one we did the clean RGB on a couple of streams ago. We did it all nice and neat, and now we're probably going to have to rip all the neatness off because we'll probably need to get under here. But we've got customers that have used, well, I say the customers, they're using other mods at the minute, but other RGB mods, and I've recommended starting with the clean RGB. And then there's a load of noise on different revisions of Mega Drive, all have different kind of noise. So I figured it'd be a good use case for the oscilloscope again, so you guys can see how to, again, I think really the best way of learning oscilloscopes is just real world usage, like just find a problem and show it being used in that actual problem. So it's a perfect use case for that because video noise is quite hard for some people to find, and it's a good use case for an oscilloscope basically. So don't know how far we'll get. Like I say, I've got pretty much a hard stop in an hour, but we'll see what we can do. So we've got the ground for the oscilloscope when we need it. It's flopping everywhere, so let's put that there. Evening, welcome in. It's just going to be a really short one. Like I said, we've got just an hour today, and then I've got to knock off today, but we'll get somewhere. So one thing when we're probing for noise on video signals, don't connect the oscilloscope, like for now, in terms of visualizing, because you can add noise to the image when you connect the oscilloscope. So we want to just see where we're at first without the oscilloscope connected. So let's see, this is just a stock VA4, which is apparently one of the worst for video outputs, and from what I've read from people just on Discord telling me, I don't think anyone's solved the noise on the VA45, at least not all of it basically, just some of it. Morning from Texas, welcome in. Brand of solder mask. I use, just to be honest, generic stuff, so AliExpress. I've actually, I think this might still be one of the first ones. It's normally called 3-second solder mask these days, but this is just a generic brand off AliExpress, for example. But if you type in 3-second solder mask, that's normally what they're now calling them. But to be honest, I've recently just gone to just nail varnish UV resin. So this is just what they sell for nails normally on, I think this was Amazon. So just go to Amazon, type UV resin, you'll probably see this. I'll just drop this on with a cotton wool bud and cure it, and that's what's literally on this board that we did. So this is the resin, and you can tell it's basically the same stuff. It's clearly, this is what the 3-second solder mask is. They've just probably rebranded it. So if I put some next to it, this is the actual UV nail varnish, or not nail varnish, UV nail stuff, and this is the new stuff. So we just put that next to it, and just put a bit on. We're probably gonna have to, like I say, break this off anyway and cure that on. You'll see it, you can pretty much tell it looks exactly the same as it is. Cure over it. Now you can see this UV resin here is actually reflecting the UV light, whereas this one isn't, so it's not going to be the same product. But so that's gone rock solid, so is that. They feel basically the same. The only difference is this one kinda, you can see it absorbs and reflects the UV, whereas this one doesn't. So they're obviously a slightly different product, but for just tacking down and covering stuff, they both do the same job really. And I think the kind of gel nail UV resin stuff is just way more popular and common than solder mask cover, so you'll probably find it easier doing that. Portrait, oh shit, yeah, portrait stream's still live. I was going to say I normally edit the portrait streams to stop non-subs joining in, but I'll just leave the portrait one open. It's only a quick 1-hour stream, so we'll just leave it open to the public on the portrait for now. I forgot all about that. Right, so first thing we want to do is pull up this, and let's just go to Test Suite, and let's take a look at what noise we're dealing with. So pull this up here. Whoa, yeah. So see all that vertical lines on the greys. Greys normally show it the worst. And if this is noise introduced by RAM, you'd normally find going between pages the noise changes. This seems fairly static. So the noise isn't changing as I'm using different things and going between pages. So that indicates it's got nothing to do with RAM, or at least this current level of noise has nothing to do with RAM. So short of just probing around in the dark and having no idea basically what you're doing, the way I identify noise is, I'd like to think, pretty common, pretty obvious, but not many people seem to know. When you look on the retro scene, as always, no one seems to have much knowledge of what they're doing, basically, and they just try random things and put caps in random places, cut random traces. It's like, no, don't solve noise like that. Just look at it on the scope and figure it out. So it's exactly what we're going to attempt to do. Now I could eat my own words and fail at this miserably, and we don't find the cure. But let's start with the oscilloscope and see if we can find the noise. So what I want to do ideally is to get something on screen. Can we just get like a white screen with noise? That would be perfect. Color bars, color bleed, reference color bars. Now I can never remember where the white and RGB screens there. So white doesn't show noise because it's bleaching everything out. So is this where we can do certain buttons too? There we go. So I can bring that down to a grey, and there you go, you can see noise. So perfect. So that now is a nice static screen. Well, I say static, it's almost static because we've got them random numbers on screen. So can we hide them? Of course, that toggles between screens. There we go. So now that is basically a perfect flat screen. So what we want to see on the scope is we can trigger on sync. I probably want to solder onto, well, let's just probe the red in first. And how am I going to do this? Because we've got that. Well, you can see what's on screen. You don't need to now see that, basically. That's what you're seeing on screen. So let's go over to the scope instead. There we go. Set this thing up and let's take a look at what we're looking at. So set this up to about here. So the inputs you can see are quite noisy as it is. So they're going to be probably the lines. But considering the noises on the output, and the output is DC offset and corrected, and a bit easier to scope because we can get to the 0 DC and scale it, we'll go to the output like that. So what I'm going to do is just solder a wire so I can just grab the scope on this red. So I'm presuming the red, green and blue are all going to have similar noise, basically. It might not be the case because this is almost likely introduced by what's typical is like clocks and trace runs and things. That's normally where the noise is. So I'm just going to pick red for start with. I'm going to solder to this point on the clean RGB, which is the DC corrected output. And now I can just grab the little thing on the probes here. So I've got a hand free, basically, to do this. Would it be... can you help with my PoE camera? Don't think that's a sub, maybe. At the minute, this is a sub-only stream, by the way, so if you're not a sub, you probably... Well, basically, if your comments don't pop up on stream, it won't be really answered for now. If you are a sub, just pop up a message again, it'll pop up on stream. We've got it open to the public on vertical YouTube at the minute, just temporarily. Would it just be caps on the OG Xbox if I'm intermittently getting noise? It's kind of like when you've been playing for a while, you start to get dots. Usually, anything like it's not always, but usually, yeah, anything time-based is normally caps warming up and expanding, or something warming up and expanding. It's not always the case, but it's normally that. Right, so where's my mouse? This is what we're looking at, and I'm almost guaranteed that this is going to be the noise, but we haven't really got a stable trigger here. So there we go. We'll go on this random undershoot on the sync pulse. That seems to now lock into it's really hard to lock into here because we want to see the noise. We don't want to filter out anything. So now if we go to a really fast scope, what we need to try and see is, do we have any harmonics? So if we drag that over you can see here, look at this spike wave here. So this is ideal, what we want to see, something repeating. So we just pause that and drag out between these, and let's see what the gap between these is. So you can zoom right in. You want to be really accurate because this will give us an idea of what we're looking at. These two peaks here, look at that, 3.354 megahertz. So once you start doing video signals, that I can tell you straight away is a clock. So we've obviously got like a 53 meg here, but let's pull up the schematic. And I am sure well, I know it is because I've done so many of these video mods and things. We will find Mega Drive. Are we on a Mega Drive 1? Yep. VA4. We have schematics for. Pull this over here. Now, because we've got noise as like one of the noises is 3. Let's close that down a second. What did we say it was? Close that. 3.354 meg, and that's a pretty accurate measurement. We need to now look for something that's got a 3.34 meg clock. Now the problem is this is quite a bad schematic to try and see because everything's really blurry. So what we could do is maybe, do we have a redrawn Mega Drive schematic, even though it's a different revision? Let me see if I've got a redrawn schematic in that folder. Mega Drive. I'm sure there was a redrawn one. Mega Drive board keycard. So somebody's done the PCB layout. Have they done a schematic? Let's open it up and find out. So, keycard schematic editor. I presume they will have. And this will give us a nice way. It might not be, like I say, the exact revision, but it will give us hints of where to look. The other thing is you can just look around the board for clocks. Right, yeah, so we have this now. This is keycard. So somebody has redrawn this. And this is like basically the schematic just sort of dumped on the screen, but it's better than the one we have. And we can look around for, what I'm going to look for is clocks, DC jacks, power in, video and audio. So I'm almost guaranteed it's going to be something to do with video. CXA chip. So we have a clock here, clock in and out. Let's start with him and trace him. He comes up to a sub-carrier pin, so there's no clock directly with that frequency yet, but chips might generate the frequency. So the first suspect, and what it is on many Mega Drives, and we might as well jump to it and see, is this sub-carrier pin 50. It's normally a crystal that changes chroma. You can see it comes out of a chip on pin 50, comes down here, we've got this cap here, it goes through a resistor R24, then through another strange, what's that? That is a, is that a high pass? It'll be a filter anyway. It's an RC filter of some kind. I'm just looking at the schematic sideways because it's upside down, but you've got this filter here that's also on the pins. So you've got a resistor to ground, then a cap, as opposed to a cap and then a resistor. So that will be, I can't even think of the top of my head. It's either high pass or low pass filter. Then it's going through this cap again, comes up and goes into the XO in, which will be a crystal. So my guess is pin 6 on the CXA chip is going to have that exact frequency, or it's something else. We can go to pin 50 of the chip that will be under, actually, that will be directly under this here. So why don't we, we're going to have to, well, we can either lift that up, or the other problem is, let's get that shell out of the way, we have the CXA chip under here. So as we know, the CXA chip is behind this, basically, so it's under here, but we don't want to take this off because of the heat. So we could flip over the board and probe underneath. So let's take off that. I want to just cover this ground wire here so it doesn't float around and short out. And cover that for a minute. There we go. Let's check it's still running. So, yep, that's still running. So now we go back to the... Oh, just as I said that, have we knocked it off? course I tapped I tapped this ground on something. Let's just go to, well, ignore that now. We've seen what's on screen. We've got a capture. We know it was 3 point something. So I'm going to flip this board around, try and probe on the underside of here now, which is pin 1 is at the top. So what did we say the pin was on the CXA? Pin 6. So it will be the 6th pin down on here. And then we can just pull up the scope, and we're looking at the chroma crystal in then on this. So minimize them two. So remember 3.354, that's this peak here, and then you can go to this peak here, which is 3.3, and then again get really accurate. Go to that dip, and then go to the next one. 3.361, so we're very close to 3.3 something something. So if we press run now on the scope, and we go to pin 6, 1, 2, 3, 4, 5, 6, nothing. Are we probing right? Yep. So 1. Oh, that's got noise on as well. That's got the, in fact everything's got that noise on. Well, not everything, but yeah, there's that noise again. And this could be power supply or anything yet, we don't know. So we'll go into the dip of that. Go into the dip of that. Yeah, 3.3. We've got some noise everywhere at the minute. Yeah, afternoon from New Jersey. This is just a quick live, running going to be on for an hour. But have I got these pins backwards? Pin 1, 2, 3, 4, 5, 6. No, pin 6 should be. Or is that keycard thing, did we read it right? Pin 6 is the input. So yeah, apparently pin 6 on this should be a chroma clock, and we're not getting anything. 1, 2. Well, let's see. I've got the pin out on the wiki I could pull up, but I remember the top was something like ground. The next one was red, so we should be seeing some video signal there. Yeah, so there's video signal, so there's red, green, blue, and that's what we had the noise on, which you can see it's all through. So 1, 2, 3, 4, that's 5. Oh, so 5's got it in. And so, oh, it's there now. Oh, it's why, because it was capturing up here. So that is the chroma in. So let's take a measurement of that. And what you can do as well, you can use 2 probe leads, and you can probe them both at the same time and visually see if they match. But the problem you'll do with that is that your probe leads will interfere with each other, and you'll actually get coupled noise into the signals. So unless you have a very specific scope, which I think I have, I wouldn't recommend using 2 probes. I'd do 1 at a time, because like I said, they can cross communicate. And there you go, look at that. So even though this has also got some more subharmonics on that we might have to look at, but 3.367, that's as close as it gets. So we know the noise is coming from a chroma input, or at least some of it. The other concern is we have some really high frequency noise, which might be outside of the range of. The problem is with composite and RGB is the receivers will filter out normally anything above 4 megahertz. So this is just within the range of it not being filtered out. But you can get harmonics, even if you've got like a 30 meg crystal. You can get what's called harmonics, where 15 megahertz, 7.5, 3 point something, it'll divide down, and you'll get stages. Like normally six stages will still pick up, so you'd have interference. So even higher speed clocks can. And you see here we've got like a 44, so how close would that have to be? Because we've got a crystal on the other side running at 53 meg. So I'm wondering whether this high frequency noise here is also partly that 53 meg crystal noise. Yeah, so look at that. Go between them tiny gaps, you've got a bit of the 53 meg crystal noise. So all these wrinkles across the top are this crystal. And then you zoom out, and then you got this overlaid noise, which is then the chroma. So you've got 2 sources of noise already on the video signal. This should be as clean as possible. Now, if you weren't sure whether that was going to appear as noise on your signal, you can probe, say, this signal, and we might have to zoom out to find out where we are now. Bring this capture down. So this is the red channel, say. We just got random stuff on. If you weren't sure whether this noise is actually going to appear on the visual screen, the trick you can do is go to, if your scope's got it, we're going to go to digital signal processing. I'm going to apply an active filter of around 4 megahertz. This now will give you almost a visual of what you would see, or what the receiver, in this case the TV, would see. And as you can see there, the really fast 50 odd megahertz, see that noise there? That gets filtered by the receiver if it's a good receiver. But we should see that part of that 3 megahertz would still be present, because this should be a solid straight line. And see how that's like a bit wobbly? That should be a perfectly flat line. So if we were to look somewhere around, probably need to zoom out to see. Probably need to go a bit slower than that. See these little lumps? It's almost like they're filtered out. But I bet if we go on the peak of 2, if we can see it, we know what we're looking for. So say that little peak there, actually it's easier when you're zoomed out. That peak and that peak, there you go, you can see 3.8. So if I go full screen, that one, is it? No, that one. See if I move them out the way, these lines. See these 2 little dimples, the little one there and the little one there. That is the residual, if we turn that off, of the 3 megahertz noise. And see how it actually cleans it up quite well, so you can see hidden noise inside. And this is simulating what the receiver would see. And you can now fairly clearly see this up and down and up and down. This will be them vertical lines of noise. So if we try and get to the screen again, just so we can get a nice visual, and I'll show you that. We know now there's already 2 forms of noise that we need to try and clean up. But let's get as just a solid white layer so we can see. So it's test patterns, white and RGB screen, button C, go down even, something like that. So now if we capture that on the red instead, so if I probe the red, go back to the scope and then press play, you can now see, I presume, we zoom out, see there's the perfect white. So the dip is the sync in between frames, and this big long top piece there, this is the white screen with the banding in. So we can now zoom nicely into that, really close, and then we could see this is the white screen, and see all this ripple, and this is with the filter on. This is telling us these ripples will visually appear on screen. And then if we swap to that, you can see there's the exact ripples. So that's what we're seeing. Like what you see on the scope is what you see on the screen. So we know this is a perfect little capture here of the noise that you're seeing on screen. You can turn on and off this filter as part of the capture. So see how hard that is to see. If we put the 4 meg capture on, and then we go to a certain wave, and you can see it's hard to see, but this lump here and then this lump here, the peak, these are the 3 meg, but you can tell by how random they are that these peaks have got harmonics in. So that one's 8 meg, for example. Say this wave to the tip of this wave, it's got 5 meg, so there's a lot of noise in. But luckily, when we probed on the red and did this already, and zoom out, if you looked around you could find, and we managed to find, a nice little peak that we're not seeing at the minute. Maybe turn that off and then zoom in. We saw a nice little peak that we happened to capture. We were fairly lucky, I guess, at the start here. So that's the peaks we caught there, that little bit of extra noise. So how they were distinctively larger at the start here, these kind of give us just enough room to go, there's an accurate measurement. Because there's so much noise, that allowed us to get that level of detail. So we know we've got a few noises, so let's filter out one at a time, but there's definitely more than one. So we know this is coming from the chroma. So what I'd like to do here, and what I normally do, is, to fix it properly, I'll look at exactly where all the traces go, because this is almost definitely going to be traces running at certain parts of the circuit and then adding noise. So you can just redirect them and move traces around. That's one option. But a quick test to see if it's that is the chip that's generating that is going to be the VDP that's under here. So if we go to the overhead, we're going to have to take this off. It's just double-sided taped on and left up. So this is the VDP on this model, and we've got a 3155313. So if we pull up the, see if this one's got it, part number on here on the schematic. Yeah, luckily the redrawn schematic it's actually got a typo, but it's got the same part number. That's 3125313. Well, there isn't a 312, there's only ever 315. So this is going to be the same chip. There's lots of revisions. So we know from this, hopefully, I wonder if this is the redrawn traces as well. This might be ideal. Pin 50 apparently, but let me just see if this is. Let me open the full KiCad software. I don't know what revision this is, but this would be cool if this was actually a VA4 revision. That would be crazy lucky, because that's the one we want to look at. I don't think it says a revision. So this is the PCB redrawn, and no, it isn't the revision we've got, and maybe it isn't a typo. Maybe there is a 312, but I'm sure there's only a 315. I've never seen 312s in anything. So it's a different revision, unfortunately, of the traces. But this is what I'd want to do. I'd want to like lift the chip off, look at where everything goes, and then find out, literally watch where the traces go when they get close to RGB signals, or sync signals, or ground signals, to kind of clean them up. Well, not so much ground, to be honest, more power than ground, like the 5-volt rail. So this is saying pin 50, so at least we can look nice and quickly that this is pin 50 here. So if we looked at this, this is facing the same way. We can see that we're going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 pins in, basically, if it's the same chip. So if we zoomed on this, pulled focus, and then went even closer in, 15 pins in, let's see where that leads us. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So leads us to this here, presumably, this trace. So that's fairly easy to see and recognise. So if that's the case, let's turn on and probe that with the oscilloscope and see if that's what we actually see. Do we see that noise on there, basically? Evening, welcome in. Just doing a bit of oscilloscope probing. Not sure how far we'll get to actually fixing stuff, but it's mainly to get you guys seeing the oscilloscope techniques. We'll pull it back up. We'll get on the ground, which is this one. That ground's quite big. I'm going to cut that short as well, so I don't keep shorting out the board. A bit too big. That's a grip on there. Right, so are we on? No, so turn power on, run the scope again, and let's probe on that pin there then. Wow, there you go. So that's a nice clear signal. And you can see, ironically, the clock that we suspect of noise has noise on itself. So the clock, this will be the 56 meg clock almost definitely. So see that... let's pause that a minute. Right, so we have, firstly, let's check if this is the suspect. Yeah, look at that, 3.55. So that is absolutely definite. And the problem with this is that's even worse, is this is a sharp square waveform. So sine waves aren't as bad. This rapid ascent means that it does not matter what speed this signal is. So it doesn't matter whether this happens here, here, here. All that matters when you have a signal like this is the rise time. So this rise time here of 11 nanoseconds, that is damn fast, especially for an old system. So this 11 nanosecond rise is where your noise gets introduced. It's not this, it's not the fact it's 3 meg and it starts over here. It's more so the fact that the rise time is fast and sharp that you get a lot of noise. So you can do, basically, we could do like smoothing of this if we could control the signal. Put a cap on to smooth and filter it into a sine wave. You could make the signal weaker. You could do all sorts. What we don't typically want to do is remove the signal completely, because this is for chroma, for composite. You don't want to lose composite. And I did the same thing for Neo Geo. Nobody had managed to keep the Neo Geo composite and clean up the RGB. And now on retro6.wiki, you've got a guide on how to do that. So what we want to do here is try and keep this signal. We can prove that the noise is that first and try and remove it by removing the signal. And then we try and reroute and keep the signal clean. So that's one thing we'll do. But on top of that, let's also see, let's just prove that this, I presume, is the 50 odd meg crystal. So if we go to there, yeah, so you see between the two peaks there of that noise, 55.7, and look down here, there's a 53.6. So if we zoomed in, knowing that that's what we presume it is, and corrected this to like 53.6, let's see what it would look like. So it would look like about there between two peaks, and you can see, give or take, the accuracy of the scope, it's quite clearly going to be that as well. So we're not too concerned about this noise yet, but there's clearly noise on the whole system everywhere. Let's take a quick look as well at the power rail. Let's just see what the 5-volt rail is doing. So 5-volt rail in, and you can see that's not too bad. There's noise on there, but that's pretty clean. So we don't have, I don't think, too much noise on the power rail. So we should be able to clean up the clock noise as well. Benefits of this over triple bypasses and things. The bypasses don't really do anything. They're just people chucking mods on that they genuinely don't do anything. They cut traces, they move things over, and then they output the RGB with the wrong resistance values. So they'll work, and that's been the standard for a while. But firstly, the clean RGB will tap into the signals. Using all these dials, it'll remove the offsets and all the need for capacitors if there were capacitors at the output. Give you the correct voltage on this output. So if we went out and bring that down, don't even know we've got this console turned on at the minute. On, off. See what's on screen. Do we have anything on screen at the minute? Black screen, we haven't got a game in, so I'll put something in. So we then have on this one, you have ignoring the noise. If we just filter that out a minute, so you can kind of see a bit cleaner. A proper RGB signal is 0.2 volts above ground. So you can see there, 0.2 exactly. And then this should be unattenuated 1.4 volt range. This signal is, however, where I've probed the attenuated one at half that. And this isn't necessarily white. So this will be perfect RGB output without DC interference. So for one, you know the output is 75 ohms, which is what you need for all the filtering to work. So all this talk about removing this noise, all this is kind of pointless, because if your final output stage here isn't 75 ohms, the receiver won't filter that 4 megahertz. So on, say we capture this, and if I zoom in a bit, capture something like this, and then show you what we're looking at. What I'm simulating here with the 4 megahertz is if your output load is 75 ohms, and the input, the receiver, the TV, the CRT, the OSSC, it has then what's normally like a 470 picofarad capacitor. So this, in line with then a capacitor to ground, exactly those two values forms a 4 megahertz filter. If the resistor here, which is very common on many people's mods, is say 400 ohms or 150 ohms, this filter, instead of being 4 meg, results in say 2 meg, and you get softening or smoothing of the curves. Or worse yet, it results in say like a 15 meg, and you end up with spikes which appear as harsh bars. So you can see how much the accurate filter, see this is inaccurate, this is like a 150 ohm resistor. You come down, that is a perfect 75 ohm resistor. You lower the resistance lower, you get soft images. So people underestimate how important the correct RGB output is. No mod that I've seen does this right, and this is why I kind of made the RGB mods. Every mod I saw was doing it wrong, basically. Clean amp will definitely come after this as well, because these have got bad audio, but we'll start with the RGBs. I want to try and get them as clean as possible. So we know where the problem is. Well, one of the problems, and it's going to be this subcarrier signal, which is basically called a chroma clock. On this board, it's called a subcarrier. So let's try one thing first. Now, we know that apparently this is, we're presuming this chip is generating that chroma signal. So let's prove it first, and let's just lift the pin of this chip, which, to be honest, I probably want to do this under the microscope, because depth perception is non-existent if I don't use the microscope. But let me see if I can do this without getting the microscope out. I should be able to. It's quite a big chip, but let's see. Bit of flux. Warm the flux up. Alright, so what I want to do is get this tweezer that I've bent into shape, put in between there, and then now I've got a bit of leather. It's not even attached. I haven't even desoldered it yet, and I can lift it. So either I'm pulling the trace off the board, which I think I am, or it was already partially off. So you can lift up a couple of pins like that if it helps. You can see under the board there is two traces, so let's try and separate them. There we go, and then I can now separate the legs in the air. There we go, and now we have two floating legs that you can't really see too well because, like I say, you haven't got depth perception on a flat 2D image, but can we get that at a good angle so you can actually see what I've done? There you go. So I've got two legs in the air, completely separated from the traces underneath at the minute. Them traces underneath, are they still good and separated? Yeah, they are. So, a bit dark on the picture for some reason there, but they are separated. Now we need to put down the other leg back down, because that is now floating in the air and it's got nothing to do with the carrier pin. So that's the other leg back down, and now we have this leg, which we could, I don't want to bend it too much because you'll end up snapping it, but you can see I can go under here and it's completely floating off the board. So now we have a trace at the bottom, which if I just grind away the via, so we've got a nice easy pad to tap onto. Or to probe to, whichever you want to do. We now have a pin in the air. So let's see what that's done. Firstly, does it come out of the chip or does it go onto the trace? And what does it generally look like on the scope now? So if we power on, we go to the scope, and we'll turn off all filtering, so it's just the raw signal. Overlay the scope. Yeah, there's noise with the clean RGB at the minute because this is not the RGB. Like, the clean RGB will clean up the RGB signals in terms of it will filter for 4 meg output. This noise is under 4 meg, so this is unavoidable. If you were to clean this up with just the clean RGB, you'd be filtering real visual data on screen. So the clean RGB gives you exactly what the RGB should look like on the console at the perfect level. And then these noise things I always do then afterwards, I write on the wiki, identifying the remaining visual artifacts on consoles and how to fix them properly, basically. That's what I tend to do. So we can see there the top of this trace is generating that subcarrier pixel. And then if we now go to the trace below, you can see it's pretty much completely gone. So now this trace is not generating that. So let's see what it's done to the RGB signal. So let's see what it's done to the R. And you can see it looks, yeah, it looks cleaner. It looks like we've got other noise. So let's see what this actually looks like on the output now. We are on this one, and I don't know whether we've, let's get into game. I've got it plugged in. And all this is doing is proving if that pin trace is the problem, the noise will have gone. If it isn't the trace, then it could be the chip internally or more noise. And you can see that's done next to nothing. So even though we can actually see on the RGB signal output there's less noise, it still looks like it's picking up basically just as much noise. So what that means is, even though it's on the red, green and blue, let me try putting moving that chip around doesn't change anything. That means the one thing that people overlook as well on this quite easily is you don't just have your red, green and blue. So there's the red, and you can see that noise is mostly gone. Like it's not clean because there's, well, it might be clean, there's like spikes, but let me zoom out a bit. Let's first go to that nice static screen to do this easier, which will be, I think we can just press start. Oh yeah, we're already in it. So there, test patterns, white, C, down, 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 down. So that's the screen we like looking at. Let's pull the scope up for that, and now look at the red. So we can see, we know there's noise on there still. We're suspecting it's still that 3 megahertz. Where's my mouse? And then if we look in, you can see the noise is definitely reduced, but it's still also definitely there. Now, whether this is the 3 megahertz signal, we're not so sure. This might be now, even though you've still got noise on, that might not have been the major carrier. So what we're looking for is this being roughly about this far apart. We're looking for peaks that are roughly that size, and you can see you can't really see many. So maybe there to there is one. Yeah, so there's one. So you see that little dip there, and that little dip there. So we've moved out of the way. This little dip here and this little dip here are the noise, and you can see now how sensitive. If we were to scale this up, oh, there you go. Scaling it up really helps to see. The noise is still there quite significantly. So that's why it helps to also scale the scope as low voltage as possible, and there's the noise. So we're still very much in noise. So there's noise, there's noise, there's noise. So it hasn't removed that clock noise, even though clearly that clock is coming from there, which means we likely have more than one source. So we're onto the right track. We definitely know that the pin under here is, if we lift that up, this pin under here is definitely the source originally of that noise. Now, bear in mind, I did say that you can get noise that is harmonics. So you might be dealing with another noise, like for example this clock, that scales down inside this chip. So this chip is going to receive this fast pulsing clock in here. So the problem we're going to have is inside this chip there's going to be clock networks, and if those clock networks run across there, then that would be a problem. So yeah, funnily enough, you've just commented on what we're next about to do. The next thing we want to do is potentially ground this pin completely, so that inside this chip we disable, or we effectively try to disable, this pin being able to be driven up and down and completely remove that clock source. So if we looked at the scope on here, you can see you've got that clock source there. So if we were to ground this, and we could find like the closest ground, we want to see if does pulling that to ground remove the noise. It's not really a solution, but it's a brute force to find out what noise there is, basically. So if we look at this pin out on here, do we still have it open? No, we don't. Let me just open up the PCB again. I want to see if there's a ground close by. So let's bring this over. Zoom into here. So we know the subcarrier is 50, where are we? 50 there. So 2 to the left is ground. That's probably the closest. So that would mean that, and it doesn't look it on this though, to be honest. Yeah, so this is ground plane here. So what we can do is probably touch with tweezers on this pin here. So literally one over, while we have this gripped on to the red channel, and we can live see what shorting it does. So if we grip that on, check at the scope on there, and tweezers aren't the best for grounding. It's a pretty crude way of grounding because this has got a bit of resistance in the tweezers, but it's a good quick test. So there's the output, and if I look on here and I ground this chip, or ground this pin rather, so it's not really doing that, but let's instead do it properly with a wire, because like I say, kind of having a floating tweezer with a bit of resistance isn't going to do as much favours. So we can see this is a ground trace right here, so just expose a bit of ground there, and we will solder this leg to ground, and that should, because obviously it's going to be shorted to ground, we probably wouldn't want to leave that as a solution because the chip could burn out inside and you've permanently lost your chroma. But again, this is all just the discovery phase. This is where we find out what the problem is, and then once we know we're looking at the right signals, then we can try and find a proper fix. All my wires decided to wrap around itself. There we go. So we'll get a little bit of wire. How do you properly test if a voltage is going through a certain cap to any other parts? I've tried before, but capacitors immediately make a short. So yeah, so you don't test caps in that way as such. You'd have to either have a frequency generator, which I've got on my desk over here. I could show that at some point on a stream, and you'd pass a frequency through it and see if it passes through. Your frequency generator will have normally a 50 ohm load in the leads that you have or internally. So you have to do a calculation based on 50 ohm load and whatever value the cap is. And then that's basically a filter. You can work out then the filter frequency, and that tells you what frequency you should be able to send through the capacitor, because that's the job of the capacitors, to have altering signals. Basically, the frequency of the signal changes the resistance of the circuit, basically. So faster signals should pass through the capacitor, slower ones should get blocked. But to test it properly, you really need to send an actual signal through. You need to send an AC wave through, normally with like I say, a signal generator. Other than that, you don't really need to pass stuff through a cap as such. You can just get an LCR meter and test it, and that's usually just as good as well. Right, so that's now with the floating pin fully grounded, I think, if I've done this right. And if we have, I presume we'd see the noise gone, and it doesn't look like anything's changed at all. So we might want to double check we've got like the right pin and stuff as well, but then again, we've probed it, so we know we've got the right pin. Yeah, noise hasn't changed whatsoever, so let's unplug that, probe on this pin, and let's see what's going on. There is the scope. Oh, okay, I've just tapped something by mistake. Let's reset that. Go back. Alright, that's got, well, yeah, actually we don't care about that, we just want to check the signal on here. So if I check on the scope, and you can see there, we've still got noise even grounding the signal. So this is desperately trying to run the signal, even though we've grounded it. It's still managed to get some noise through. So even grounding it isn't doing the full job, basically. Which means it's got a very strong drive inside this chip, potentially, because this isn't going anywhere. So we might want to see if we can somehow disable what this chip's doing. I'm going to turn the power off because we don't want to forcefully ground that chip. And let's see what this noise is. Let's just double check we're still seeing that signal. And it's still managing to pump out, which is impressive, but that's how noise works. Yeah, it's still the same. So you got the 3.5 to 3.6 here. So this is a sign again still that we have that noise on the video rail. We can also double check that by connecting to the red, turning it back on, and then running and seeing if we see that same noise. So already you don't even need to look at that much, you can see, if I move it out the way, there's a peak, and the peak is the rise here. So that is definitely where the noise is coming from. So at this point we know we've got so far, which is this pin is generating noise. Lifting it though and grounding it did nothing on this version of a chip. Now, I have heard people say that the VA4 this works on, and other ones. I actually did one 2 days ago, a VA6, and lifting and grounding this pin completely removes the noise, like almost all of it. On this board, it's doing absolutely nothing. So it could be, it could also be where we're physically running these wires, because we're running these wires along traces here. So you have to bear in mind where we're running these and where the inputs and outputs are going. Because the thing is, because there's still noise on this pin, we kind of know the noise is still there. So we might have better luck trying to move the inputs away from noise. There's multiple techniques we can do. So let's just take a look at, firstly, the ground should still be the probe's ground with nothing really on. So that's just normal ground loop noise. We're not seeing anything specific there. The 5 volt was pretty clean before, which if I just do an AC couple of minutes so I can see the 5 volt. Are we seeing any kind of... No, that's just the... That'll be the transformer noise kicking in. So that's not really got any characteristic noise on. Let's put the filter on as well for a bit of easy viewing. Yeah, nothing there. Nothing overly there. And then let's take a look at the red again. And you can see distinctively these little humps even with the filter. So these are the humps where we're getting that noise. So that's still definitely getting it. The inputs, let's try the inputs in case they're worse. But I doubt they would be. No, about the same. We do have a little filter here you can turn on and off as well. A low pass filter. So we can go to, say, the output and visibly see if that makes any difference. It's not a solution as such. It would be more of a hint. This is what enables that 4 meg filter, but it can soften the output. And then we haven't even got to looking at things like the sync pin yet, which can also carry noise very heavily. No game loaded. Go down to that one. Load up. Let's get back to that screen. I have the same model mag drive with no composite video, but still has C-Sync. What could it be? You need really the scope on it. You need to check if you have RGB going into the CXA chip, which is where, obviously, by the AV port. That CXA chip, the pinouts is on the retro6.wiki. You want to see that you've got power going in, red, green and blue going in. C-Sync, which is the output you should see, and you're saying you've got C-Sync, so you have that output. You want to check if the RGB output's on there. So it's really, this chip under here. You've got inputs on the right side here running down, red, green and blue. Outputs on the left going red, green, blue. If you're getting red, green and blue out and C-Sync out, the CXA chip's got everything it needs and your RGB cable should work. If you're not then getting composite out, you can have, there's a few more pins on there, but it's on retro6.wiki, on just the home page, don't go into a category. And it just says something like CXA 2075 upgrade or something. The pin out for the 1145 is actually inside there. So you want to check all them signals are present, but you really need an oscilloscope to look at it properly. So we're going to here, see, down, 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 down. What were we doing? We wanted to see the red, was it? The red output, I forgot what we were actually doing. Oh yeah, I was going to see if the filter actually works. So that's the screen. If I flick this filter on, see how you can see the screen flicker? So let me just make it large. If I turn it on and off, you can see the lines slightly change, because that is filtering. That's a 4 meg filter that it's applying on top of the receiver's 4 meg filter, but it doesn't make much difference. So now with that screen on, what I'm going to do is, while it's on here, we probably want to try and lift, well actually, let me just take a look at the sync pin. Just curious before we delve much deeper. Let's pull up the scope and look at the sync pin. How clean is sync? Now sync is pretty clean. So see, that's a nice flat trace, and that's because this is one of the benefits of the clean RGB. The sync, what you can do with the sync input, and I bet the sync input's got noise on. So yeah, there's a bit of noise on there. If I zoom out, see that ripple on the sync there? So if I go full screen, this is one of the main benefits of the clean RGB, why it cleans up more than most others do. That ripple's on the input. If I go to the output, see the ripple's basically gone. So that's the output, that's the input. And I can actually do a reference image. So if I just go to reference waveforms, add, let go, you'll see that reference waveform behind there. Now if I probe the output, look how clean the output is compared to the input. So that is one of the benefits that I always talk about, but the problem is a lot of people just presume you're talking shit, basically. You can see quite clearly there, the sync has been cleaned up by the clean RGB. Now I'm not going to tell you how that works, because then people will do the same, but that's removed the noise off the sync. We can't do the same for the RGB because of how it works, basically, but the sync isn't the problem. So we are dealing with RGB having noise, because we can still see the noise. If we delete that reference wave now, which is there, remove, start up again, we can clearly see that spiky noise is the problem we have. So those big spikes are the noise we're currently dealing with. And we want to now go to a chord, remove. I tell you what, let's remove the red wire going anywhere. So let's lift that up and see what that does to the probe, at least, like the noise on the scope. Nothing at all. So it's not the output, you know, going from here to wherever it goes. That's not the issue. So we can put him back down. And what we're trying to do is just find out where the source of this noise is potentially coming from and things we can do. We know ultimately that we need to focus, you'd expect, around this chip. There's a few things you can try. So you can try to firstly, like, you know, lift up pins, remove the sources of noise. So lifting this pin up should remove the source of noise, but not necessarily. So I think I've managed to short out the console again there with my floating pin. So let me see if anything's on the screen. Yeah, turn it off and on. So now one other thing I'd do is, I don't want to just jump into, this is where I say people will just blindly try things like adding caps all over the place and trying to add debug caps. Those things can be useful and we might try them, and we probably will at some point. But before I do that, I'm still more intrigued. Like, what I'd probably want to see now is, where do these RGB traces go? That's kind of my next thought, is I want to see where the traces run, because if it is the fact that it's the traces picking up induced noise, then it gives us a hint of exactly what's wrong and where. So the next thing I'd do is probably go, where is the RGB on this chip? And then we'll lift the pin up of one of them and see what the noise is like on the lifted pin. So I've got to go in a second. We'll carry on with doing this probably tomorrow if you like. We might do it on a public stream, or we might do it on a sub-only stream. But the next thing I want to do is look for the RGB signals. Probably easier to look at the schematic first than straight on that chip. So RGB in, comes through here, goes along, and it's pin 27, 8 and 9. Oh, I've got the wrong screen up. You guys can't even see what I'm babbling on about. Been looking at the schematic. I went to the CXA chip here, RGB in, went over, and found that they go to pin 27, 8 and 9 on the chip we're looking at, the VDP. So that's the VDP there. So then if we go to this chip, we can now zoom in and look for 27. So here we are. So 27, 8 and 9, we've got 1, 2, 3, 4, 5, 6. So we want 6 pins up on here. We want to probably, we're going to have to pull this UV coating off if we can. There we go. So UV coating out of the way. And what pin did we say? 1, 2, 3, 4, 5, 6. So 6 pins up. We want to lift that pin up. So we have 6 pins up. Flip this around. This is not the right direction for me. 1, 2, 3, 4, 5, 6. So this pin here, which is definitely a microscope job for me. Let me just do this under the scope. You can just wait there a second while I do this. I'm not going to set up all the camera just for lifting this one leg up for now. It's in a right awkward position. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 there. So get that behind, lift that up. Right, so he's in the air. And now what we have there is this will tell us if the noise that we see stops when we lift that leg up. Then it's the traces coming off here that run somewhere that pass by something that induce the noise. If we still see the noise on the pin in the air, then the noise is coming from inside this chip. Pretty much is like, well, either the noise is coming from inside the chip, or this chip is picking up noise on its power rail that then couples into the RGB. You know, something along them lines, basically. That's where we'd be at. So, that's turned on. Mouse, where are you? What do we want to do now? I want to check on screen if we're still running. Yes, we are. We're missing the red, obviously. We'll go to... of course, we've not loaded the game, so I keep managing to reset this flash card. Load that in. We'll get to that white screen so we can see just the same thing. Test patterns. White. C. Down, down, across, down, down, across, down, down. So obviously that will look greeny, but that's because we don't have the red. So now with that on, as long as I don't short things out, we go back to the scope, and that's still running. And then now what we want to do is probe on the floating red pin. Ooh, look at that. Nice and clean-ish. I'd say it's clean. That looks pretty clean. Let's turn off the filter now. The DSP is still on. So we still got noise there, but obviously that's a lot cleaner. So in terms of, that's the red there, compared to, say, if we go on the green. Or is it? Is it just because it's higher voltage and we're zoomed out more? Maybe not. So I guess the only way of doing that is decrease that, decrease that. I've still got AC coupling on, I think. Go to DC coupling. Zoom in. No. Still on there. I thought it wasn't, but just again, visual. So this is going to be the 3.39. Yeah. So that noise is still on the pins that are in the air. So this is probably why people haven't solved as such the noise on the, and correct me if I'm wrong, but I'm pretty sure people haven't solved the noise on the VA4 yet. So where we're up to on this is, we know this chip has this pin, and to be honest, one other thing, let me just quickly do, I'm intrigued by, is, let me probe this and cut that trace while it's on. So this is the red. That's the noise on the red. If I cut this grounding wire, ready? He says, let me get that up in the air so I can just cut it at an exact point in time. So that's the noise at the minute with that signal grounded. If I cut this wire, absolutely no difference. So by grounding the output, it's doing nothing at all. Like on this revision, like I said, I've done a VA6 and it fully solved the problem. So we have this subcarrier noise coupling into this chip itself, even on just the output leg that's not connected to anything that's floating in the air. This output leg has got that noise coupled onto it. So we have a fairly big issue we need to try and solve there. The next step, like I say, I've got to go for now, but the next step will be, we'll probe every single pin on this chip and look for any clock signal that matches the subcarrier, because there might be multiple, and any harmonics of it that might match. But the thing is, this clock will be derived from this clock anyway. So it could be this clock's noise, and it's purely this clock's noise with harmonics coming down. And we might want to soften that crystal. So it just basically needs a lot more probing. So this crystal will have, I mean, you can just touch on the cage and see the noise. This will be the 50 odd megahertz. So if I zoom in, you don't even need to probe on the pin, you can just touch on the cage. And then you can see there's one, there's another, and there's the 51 megahertz. It's 53, but obviously zoom in and correct it a bit more. There's your 53 megahertz on the clock. So this has got noise. Now the harmonics are bigger spikes, so you can see these slower ones are the harmonics, and what you can try and do to see the harmonics is, again, get a filter, activate it, and there's a 4 meg filter which you're going to see these harmonics from it. So in fact, there's the 7.4 megahertz, and if you went to a half, actually if you went to a double, look at that. So obviously it's fairly obvious because this clock generates that clock, it does internally, but the 53 megahertz clock has harmonics that are 3.5, and this is coming from the clock, and you can see that because we've put the filter on. So if we turn the filter off, you're not really seeing very clearly that there's an overlay of that noise there. So if we turn it on, you can see that now it is, and if you capture on a signal, you might be able to sort of stabilize it more, but you basically pause the signal, zoom in, and then pick a point. So you've got that, and these are all harmonics of that clock. So if you times these frequencies up, like 3.3 into the 53, you'll find it's more than likely a division. So I think the noise on this is potentially this crystal here. We could prove that by lifting this chip off, feeding it in with a signal generator, and changing this frequency. Now the system will probably not work right, or overclock or underclock, but the point would be, if we adjusted this clock, does it adjust the noise and the bars on screen, and do they move? And if so, we know the noise is potentially just coming from this, or this noise is coupling in somewhere else and we follow this trace. But that's where I'd want to get the bare layout of a VA4 board. So what I'd normally do, and if I had more than one VA4, which I might do, I'd strip the whole board, sand it down and see all the traces, or just strip the board, I think it's 2-layer, and look at where all the traces go. So it involves a lot of work, but that's how I'd solve the noise properly, and that's how I did like the Neo Geo and things. So we've identified where at least one part of the noise is, and obviously we've not found a solution yet to even reduce it at all, but we know where to look, and we know what we want to do. We know the next steps. We want to take it kind of systematically and try and solve it properly, so we know where the noise is introduced, and then fix it without having to ideally lose composite. That's the goal. But I presume you can also see how much more useful using the oscilloscope as a real world example, like me just probing around and you watching how I lock onto signals, how I'd use it, stuff like that, is a lot more useful than me just telling you where buttons are on an oscilloscope and you kind of following and going, oh yeah, that's I like that, and I can click here and I can do that. If you haven't got a goal when you're trying to learn, it makes it a lot harder. But having that goal to say, we want to find this video noise, and this is how we're going to lock onto it, and this is what the filters are for, that will stick in your memory, a lot better. So that was just a quick rundown of, the start of investigating the noise on the VA4. We'll certainly get to the bottom of it. It's just time permitting. Obviously, absolutely mental busy with the Christmas rush, but let me know if you maybe want to just keep doing this on the sub-only streams and working our way through this board and trying to identify the noise on this board, or whether you want to do other things, or maybe, like I say, some work on a Tuesday or Wednesday and the other day, maybe one day working on this and the other day working on consoles. Just let me know. But yeah, that's it for this one. Just a nice quick one, like I say. And I've just got to get off because I told the missus I was getting off for dinner at 6, and I'm already like a quarter of an hour late, so tea's probably cold already. Yeah, definitely. There's a lot. The thing is with the Mega Drive, I think I've done something on the wiki. Oh well, I know I have because somebody told me on the Discord that I've already solved most of these noise problems, which I can't even remember doing, to be honest. Sega Mega Drive jail bar fix. Yeah, so there's overlay that. You can see on here we've got very distinctively a similar noise. I must have identified the problem at some point from the subcarrier. That is even lifting the pin that looks exactly the same as this revision board. Well, is it the same or is it just very similar? Because like I said, there's loads of revisions. I presume it's not the same because it hasn't worked on ours. Where are we? Yeah, it's not quite the same. So see how we've got a via and then a ground plane pointing at it, and on the image it's just like, you can see there's a difference. But on this one, whichever one I did at the time, I obviously must have probed it, seen exactly that, and then cut the trace to solve it, and it completely went. So we know we're on the right track in terms of noise, but every revision's different. So there's another problem here that we need to find, and there'll be a difference. The worst case is if this actual IC inside has, say, the RGB traces on the actual die inside running too close to a clock circuit, then you're almost screwed. There's some things we can do to help, but that might be a permanent problem. I don't think it's going to be on this. I think we'll figure out what it is, and I just think it's another issue with another clock trace that nobody's figured out yet. So yeah, I'll catch you guys probably tomorrow.